Let's consider a counting problem from IMO 1969, question 5. Given that there are more than 4 points in the plane, such that no 3 collinear, prove that there are at least n-3 choose 2 convex quadrilateral. Those vertices are 4 of the given points. Before we begin, so let's clarify with some of the terms here. We will say that 3 points are collinear if their straight line pass through these 3 points. So in the given condition, this is not allowed. A quadrilateral is a polygon of 4 sides. For convex quadrilateral, this is one of the example, and this is one non-convex quadrilateral. For n equals to 5, this is a base case. We'll consider any 3 points. We will form a triangle because no 3 are collinear. If one of the points lies in this region, then we are done. Or this region, then we are done. Okay? If not, then the 4th point and 5th point has to be in here, either these 3 regions. We can draw a bigger triangle like this if the 4th point is on this region, likewise on this or this region. With this, we can actually just consider that we start with a triangle and the other 2 points inside the triangle. If it's not inside the triangle, we can have a bigger triangle that includes this initial vertex. Then we can form a quadrilateral, a convex quadrilateral using these 4 points. So we will have one quadrilateral if n equals to 5. And if n equals to 5, n minus 3, 2, it will be equals to 5 minus 3, 2, that is equals to 1 if n equals to 5. So once we have a convex quadrilateral, we are done. So for n greater than or equals to 6, we'll consider the number of convex quadrilateral. And how to consider that? We know that for any 5 out of n vertices, there must be at least one quadrilateral. For example, if n equals to 6, 1, 2, 3, 4, 5, 6. From this 5 point, we will have one quadrilateral. The quadrilateral may come from vertex 1, vertex 2, vertex 3, vertex 4, not vertex 5. Okay? But with these 4 vertices, V1, V2, V3, V4, later on, the same quadrilateral will be calculated again and again. And how many times it has been calculated? It has been calculated for n minus 4 times. So the number of convex quadrilaterals will be greater than or equals to 1 over n minus 4 times n choose 5. Our task now is just to prove that this value is greater than or equals to n minus 3 choose 2. And this is not difficult. And this is equals to 1 over n minus 4. And this is n minus 1, n minus 2, n minus 3, n minus 4 over 5, 4, 3, 2, 1. n minus 3 choose 2 is actually n minus 3, n minus 4 over 2 and 1. So it's actually come from here. So now we left with n minus 1, n minus 2 over n minus 4, and this is equals to 60. Let's consider n minus 1, n minus 2, minus 60, n minus 4. And this is equals to n cubed minus 3n squared minus 50n plus 240. And this is equals to n minus 6 n squared minus 40 plus 3n. And from here, this is easy to see that this is greater than or equals to 0 for all n greater than or equals to 6. Then with this, we know that this term is at least equals to 1 if n is greater than equals to 6. So this will be at least greater than equals to 1. And this is actually equals to n minus 3, choose 2 for all n greater than or equals to 6. And therefore, we have proved the statement. That's the end of this question. I'll see you again next time. Bye-bye.